Welcome. We're going to continue with the next data model. So remember, we already discussed the concepts of data modeling, the hierarchical data model, the Cartesian data model, and the entity relationship model. So in what follows, we will still have to discuss the enhanced entity relationship model, the relational model, and the UML model. So we're going to start with the enhanced entity relationship model, the EER model. Basically, what the EER model is going to do is it's going to build further upon the ER model, and it's going to add a few modeling concepts on top of that. A few modeling concepts that will allow us to model more of the aspects of the universe of discourse. And the modeling concepts that we're going to add are specialization and generalization, categorization, and aggregation. Let's first discuss specialization and generalization. So imagine that you look at the university context, for example, and there you can think of different types of entity types. So you have a course entity type, you have a professor entity type, you have a student entity type, and maybe you have an administrative assistant entity type. Well, if you look at the student entity type, the professor entity type, and the administrative assistant entity type, you're going to see that those are all three examples of people, of persons, obviously sharing some attribute types, like date of birth, like gender, like email address, etc. What you're going to do in a specialization generalization is that you're going to take the professor entity type, the student entity type, and the administrative assistant entity type, and you're going to generalize it in a superclass person, for example. This is what we call bottom-up generalization. We could have also done it the other way around and start from the person class and specialize that one into professor, into student, and into administrative assistant. That would be referred to as top-down specialization. The relationship between a superclass and any of its subclasses is always an is-a relationship. A student is a person. A professor is a person. An administrative assistant is a person. So there's always an is-a relationship between the subclass and the superclass. Specialization, in other words, is the process of defining a set of subclasses of an entity type. So you have an entity type person, and you're going to define the subclasses student, professor, administrative assistant. The set of subclasses that form a specialization is defined on the basis of some distinguishing characteristics of the entities in the superclass. So professors have distinguishing characteristics, students have distinguishing characteristics, administrative assistants also have distinguishing characteristics. So the specialization process is going to define a subset of subclasses. It's going to establish additional specific attributes for each subclass. For the subclass professor, you can specify an additional attribute like academic degree, whether the professor is an assistant professor, an associate, or a full professor. And maybe we can also establish additional specific relationship types between the subclass and any other entity types. We can have an additional relationship type between student and course. A student can subscribe to courses, a course can be followed by students. We can also have an additional relationship type between professor also and course, but then this is a teaching relationship type. Professor is going to teach courses. A course is being taught by professors. Generalization, also called abstraction, is the reverse process of specialization. Right? So if you go from student, professor, administrative assistant to person, this is what we call generalization. If you go from person to student, professor, administrative assistant, this is what we refer to as specialization. Here you can see an example, EER specialization. So you have artist with name and picture. Name is underlined since it is the key attribute. And then artist can be specialized into painter, which has an attribute type painting technique. And artist can also be specialized into sculptor. Sculptor then has an additional relationship type to material to indicate what material the sculptor is using. So you see, by allowing these kind of specializations, we can model more of the aspects of the underlying universe of discourse. Now, a specialization can then further be characterized by means of a disjointness and a completeness constraint. A disjointness constraint is going to specify if the subclasses of the specialization are to be disjoint, That means that an entity can only be a member of at most one of the subclasses. Right? Think about the example I gave earlier, person into student, professor, and administrative assistant. A professor cannot be a student at the same time, right? A professor cannot be an administrative assistant at the same time. A student cannot be an administrative assistant. So there's a clear disjointness there. The subclasses are disjoint. An entity can only belong to one of the subclasses, can only be a professor, a student, or an administrative assistant. If it would be the case that the subclasses are not disjoint and that an entity can belong to multiple subclasses at the same time, then we call that an overlap specialization, because the entity can actually overlap between different subclasses simultaneously. A completeness constraint is then going to tell us whether any entity in the subclass is going to belong to one of the subclasses. If it is the case that all persons are either a professor or a student or an administrative assistant, then we have a total specialization. If there would be people that are nor a student, nor a professor, nor an administrative assistant, we would have a partial specialization. So that gives us 4 possible combinations to further qualify a specialization. Could be disjoint and total, could be disjoint and partial, could be overlapping and total, and could be overlapping and partial. Here you can see an example of, or I actually see 2 examples. The first example is a specialization which is partial. So you have artist, which has a partial specialization into painter and sculptor. This is clearly partial because you can have artists which are neither a painter nor a sculptor. Think about musicians. A musician is an artist, but is nor a painter nor a sculptor. The specialization of artist into painter and sculptor is also overlapping because you can have artists which are simultaneously painters and sculptors. Think about Leonardo da Vinci, for example. He was simultaneously a painter and a sculptor. The bottom half of my slide, there you have person. Person has a total specialization in man and woman. Yeah? The total specialization is indicated by the double lines. Right? So you see the double lines indicating a total specialization. You can indicate a total specialization with a double line, or you may as well add a T, the letter T, just next to the specialization to indicate that it's total. T for total, or if it would be partial, like in the above example, you just add P. Then you also see D, that's disjoint. That means that a person cannot be a man and a woman at the same time. So that's a disjoint specialization. Those specializations can be various levels deep. You can have multiple specializations. You can work out specialization hierarchies or lattices. A specialization is a hierarchy if every subclass has at most one superclass. If a subclass would have multiple superclasses, you would have a specialization lattice. Of course, if a subclass has multiple superclasses, we have the idea where the shared subclass is going to inherit from all its superclasses, and that's what we call multiple inheritance, since the subclass is going to inherit from multiple superclasses simultaneously. So in a specialization lattice or hierarchy, a subclass is going to inherit the attributes and relationships, not only of its direct superclass, but also of all the predecessor superclasses, all the way up to the root of the hierarchy. So everything is inherited from all the superclasses, ranging up to the root of the hierarchy. As we already said, specialization, so going from person to professor, student, and administrative assistant, is a top-down process of conceptual refinement, because you're basically refining the concept of person into student, professor, and administrative assistant, whereas generalization, the other way around, corresponds to a bottom-up process of conceptual synthesis. Here you can see an example of a specialization lattice. So you see we have vehicle, which is subject to a partial specialization because you have only one line there. A partial specialization into motorcycle, car, and boat, and that specialization is with overlap because you have, for example, a 3-wheel vehicle, which is at the same time a motorcycle and a car, and we have an amphibious vehicle, which is at the same time a car and a boat. So it's a clear example of a specialization lattice here, where we have the idea of a shared subclass and multiple inheritance. Remember, multiple inheritance means that the 3-wheel vehicle is going to inherit from motorcycle and car. Okay, so that was the first New concept in EER, that was specialization, generalization. Another new concept in EER is the idea of categorization. And a category is a subclass that has several possible superclasses, whereby every superclass is going to represent a different entity type. The category then represents a collection of objects that is a subset of the union of the superclasses. We also have inheritance here in the categorization setting, but the inheritance corresponds to an entity inheriting only the attributes and relationships of the superclass it is a member of. That's what we call selective inheritance. A categorization can be total or partial, and if it's total, it can also be represented as a specialization, generalization. Let us just illustrate this with an example. So here we have two entity types, person and company. And imagine that we have three entities. We have Bart, Peter, and John, and we have three companies. We have IBM, Microsoft, and SAP. Account holder is then a category class because it's a subset of the union of the entities of the superclasses. So in the account holder class, you can have entities like Bart and Peter, but not John. And at the same time, you also have IBM and Microsoft, but not SAP. That would then be a partial categorization, right? Because not all persons are account holders, not all companies are account holders. So the account holder category is basically a subset of the union of the entities of the superclasses. So we only have Bart and Peter and Microsoft and IBM in the account holder class. If, however, that categorization would be total. So it means that would mean that all persons are account holders, all companies are account holders. So in the account holder class, you would now have Bart, Peter, and John, IBM, Microsoft, and SAP. They would all be account holders. Then you have a total categorization, which you can also represent as a specialization, generalization, because then you can make person and company a subclass of account holder. Okay, because then the is-a test, as we clarified it earlier on, is going to work out nicely. A person is an account holder, a company is an account holder, and that's why we can work it out into a specialization, generalization. The idea of selective inheritance means that if you look at the account holder entities, some of them will inherit from person, other ones will inherit from company. So they will all inherit depending upon their origin. Selective inheritance is how we refer to that. Note that the account holder entity type also has an additional relationship type with the bank entity type. So that's the idea of a categorization. A third extension in the EER model is the idea of an aggregation. And aggregation means that we're going to aggregate various entity types together with their relationship type into a higher level construct. So the entity types that are related by a particular relationship type are combined into a higher level composite entity type. This is especially useful when the composite entity type has attributes on itself or when it has relationship types on itself to other composites or other entity types. This is a very straightforward extension. So here you can see a setting. A consultant can work on minimum 0, maximum n projects. A project is being assigned to minimum 1, maximum m consultants. Now, what we did was we aggregated consultants together with project and its relationship type into a higher level aggregate or composite called participation. Why? Because it makes sense to define relationship types and attribute types at the level of the composite. So you see at the level of the composite, we could actually define an attribute type like duration, which is going to tell us how much time a consultant spent working on a particular project, or we can also define an additional relationship type at the level of the composite. And here we have an additional relationship type between participation and contract, for example. Here you can see our earlier personnel administration example, but now extended with those new modeling concepts. So basically, we applied two modeling concepts. We applied a partial specialization of employee into manager. It's partial because not all employees are managers, of course. So there we have a partial specialization. We also applied an aggregation. That means that we aggregated department and project and the relationship type in charge of. We did an aggregation there into the aggregate or composite allocation. The level of the allocation, then we also defined the relationship type works on to employee. So you see, using the concepts of specialization, generalization, categorization, aggregation, you can model more of the aspects of the universe of this course. But when you come to think about it, actually many of the limitations that applied for ER are still going to apply for the EER model as well. We're going to come back to that in a moment. So how are you going to design an EER scheme then? First, you need to look for the entity types. So you're going to look for the nouns in your textual description, into the description of the universe of this course, and the nouns are typically going to refer to entity types. Then you're going to identify the relationship types and make sure that you can assert their degree. Then you're going to quantify the relationship types using cardinality ratios, participation constraints. You're going to identify attributes, link them to the entity types, link them to the relationship types if needed. You're going to think about which is the key attribute. Make sure you underline that. Think about which are the weak entity types, what are their partial keys. You're going to apply abstracts such as, or abstractions such as generalization, specialization, categorization, and aggregation, which are the EER modeling concepts, remember. You're going to assert the characteristics of each abstraction, whether the specialization is disjoint, overlap, total, partial, and also there will always be semantics that you cannot enforce. There will be business rules, integrity constraints that you would like to enforce, but which you cannot enforce into the EER model as such. And that is very important that those are appropriately documented. So I told you already that many of the limitations that we faced in ER are also going to apply in the ER model. So no temporal aspects. We cannot model that a person cannot return to a department of which he previously was a manager. We cannot model that a person should be assigned to a department after 6 months. Consistency amongst multiple relationship types. We cannot model that a manager should also work in the department he or she manages. We cannot model that employees should work on projects assigned to departments to which the employees belong. If we have integrity rules amongst multiple attributes, we cannot model that as well. If there would be operations or triggering events, we cannot model that as well. So all of these should be nicely documented as part of your business rules documentation, which is going to specify the limitations of your EER model. The ER and EER model are very nice models to capture the underlying information needs within the particular universe of this course. But of course, those models should also be appropriately implemented. A next model, which will be very helpful in that respect, is the relational model. So we're going to discuss the relational model and the basic concepts thereof. So the first author to write down the formal underpinnings of the relational model was a guy called Edgar Cott. So in 1970, he wrote a seminal paper published in the Communication of the ACM, which is a top journal in the field. And the paper was entitled A Relational Model of Data for Large Shared Data Banks. And the relational model is a formal model with a sound mathematical foundation based on mathematical set theory and first-order predicate logic. It's a model which has really a very nice mathematical underpinning. Contrary to some of the previous models that we discussed, like the Categorization model, this model is really theoretically sound and solid. Unfortunately, it does not have any graphical representation. The ER model and the EER model had a graphical representation, which made it a very nice model to kind of discuss about information requirements in a particular field. We do not have this in the relational model. It has a lot of informal definitions like relations. Relations are the equivalent of entity types. So previously we had an entity type product, we had an entity type student. Here we're going to refer to that as relations. The relational model is then going to represent the database as a collection of such relations. A relation is defined as a collection of tuples, and a tuple is an entity. Right? So you have a relation student, and you have a particular student, which was so you have an entity type student, and a particular entity student, like John, Adam. Well, here the entity type is what we call the relation, and the individual entity or the occurrence is what we call a tuple. A tuple is an ordered list of attribute values, right? Like a student with its student number, student name, birth date, etc. Each tuple is uniquely identified by means of its primary key. That could be like student number. Student number could be a primary key, which is going to uniquely identify students. Tuples will then be connected or interrelated by means of foreign keys. We will extensively talk about that as we proceed through the chapter. This is a very important model, and it has been very popular in the industry. So that means that there are lots of commercial implementations thereof, amongst which provided by Oracle, IBM, and Microsoft. A relation, remember, a relation is an entity type. So we have an entity type student, for example, or an entity type professor, and a relation can then be interpreted as a table of values, right? So it's a table, it's represented in a tabular format, and it has values. Each tuple corresponds to a row in the table, so that could be like a student tuple, an individual occurrence of a student, which is a particular row in the table. Attributes can then be seen as column names, right? So like student number, student name, those are attributes. An attribute value is then an individual value of a particular attribute for a particular tuple. That's going to be represented in a cell. The table names and column names are very useful to actually help in interpreting the relation and the meaning of the values in each row. You can see an example. So we have a relation named student. We have different tuples corresponding to individual students. We have different attributes, and we have different attribute values. So remember, the attribute values are basically the values that you see occurring in each of the table cells. A relational scheme are denoted by, as you see right there, is made up of a relation name and a list of attributes. So every relation has a relation name, student, and a list of attributes, student number, name, birth date, etc. Each attribute is the name of a role played by some domain in the relation scheme. So remember, a domain is a data type, right? The data type can be integer, or it could be a date data type, which has month, day, and year. And the domain is going to specify this data type. So DI is what we call the domain of attribute AI, and is denoted by DOM AI. R is the name of the relation scheme. So there you can see some examples at the bottom. You see student, professor, and course, each with their attributes. And as I said, the attributes take on values from a particular domain. And a domain can be used multiple times in a relation scheme. So I have a domain product number, for example. Domain product number could be defined as an integer ranging between 1 and 9,999. If I then have a relation bill of material, which is going to specify what product consists out of what other product in what quantity. Think about a bicycle consisting out of wheels, 2 wheels, and think about a wheel consisting out of spokes, and I don't know how many spokes make up a wheel, but let's say 25. Then I have a bill of material relation to model that with a major product number, which is going to take on values from the domain product number, and a minor product number, which is also going to take on values from the domain product number. So both major product number and minor product number are going to take values from the domain product number. So the same domain can be used multiple times in defining a relation. A relation, which is also called an extension for the relation scheme R with all its attribute types, is then a set of M tuples. M tuples, which each correspond to an ordered list of values. An ordered list of values according to the attributes. And every value of the attribute should be, of course, a value from the underlying domain, or it can also be a special null value. A null value means that the value is not applicable or unknown. Think about a student having no email address, for example. So you can see some tuples right there, Dick Davidson, Barbara Benson, Charles Cooper. Some of them have values for the underlying domain. Some of them also have null values. You can see Dick Davidson for the third attribute type has a null value, inapplicable or unknown, remember. A relation is a mathematical relation of degree n on the domains from attribute 1 up to the domain of attribute n. And basically, this relation is a subset of the Cartesian product of the domains that define it. What is the Cartesian product? Well, the Cartesian product is a mathematical concept which basically lists all possible combinations that you may encounter. So it's going to specify all possible combinations of values from the underlying domains. And of all these possible combinations, the current relation state is going to represent the valid tuples in a particular state of the world. So here you can see the Cartesian product by example. So we have product ID as an attribute, We have product color and category. The Cartesian product is then simply going to list all possible combinations of product idea with product color and category, and the relation that you're going to encounter in real life is then a particular subset of this Cartesian product. The Cartesian product gives me all possible combinations. The relation I will encounter is actually a subset of all those possible combinations. What are the characteristics of relations? Well, there's no logical ordering of tuples in a relation. Remember, a relation is a set of tuples, and a mathematical set has no ordering. There is, however, an ordering to the values within a tuple. So within a tuple, you're going to have an ordering of the values. You're going to have within a student tuple first student number, then student name, and so on. Each attribute is single-valued and atomic, so no multi-valued attribute types are tolerated here. And a null value, as I said earlier on, corresponds to inapplicable or unknown. Think about a student whose email address is unknown, for example. Using a relational model, you can have various relational constraints. You can have domain constraints, you can have key constraints, which usually boils down to a uniqueness constraint. You can have entity integrity constraints, not null constraints. You can have referential integrity constraints, and also some additional semantic integrity constraints, although the latter category you see appearing between brackets because those cannot be nicely modeled or enforced in a relational model. The value of each attribute A must be an atomic value from the domain dom A. So that's the domain constraint. It basically specifies that every attribute in a tuple should be a value from that domain, and it should be atomic. You see two cases there, a right tuple and a wrong tuple. So the first tuple is a good tuple because you can see that all attributes are atomic. The second tuple, you see that address is a composite attribute type, so it's clearly not in line with this domain constraint, which is the first important constraint in the relational model. Okay? A key constraint? Well, all tuples in a relation must be identifiable. That means they must be unique. You cannot have two tuples that have the same combination of values for all their attributes. Because in a set, in a mathematical set, remember, all elements need to be unique. So they need to be identified in a unique way. And the way we're going to identify them is by means of a superkey. So a superkey is going to consist of a subset of attributes of a relation with the property that no two tuples in any relation could have the same combination of values for the attributes that make up the superkey. So as such, every tuple in a relation has unique value for the superkey. So the superkey specifies a uniqueness constraint. No two distinct tuples in a state can have the same value for the superkey. Every relation is going to have at least one default superkey, which is just a set of all attributes. Note, however, that a superkey can have redundant attributes. If you look at the student relation, for example, you can have student number, student name, student birth date. That's a superkey because every student has a unique combination of those three. But there are some redundant attributes in there. Basically, you could remove student name and student birth date and only keep student number. Student number would be a minimal superkey. It's a superkey, but in a smallest format. A key of a relation is then a superkey with the additional property that it's minimal, so that means that removing any attribute from the key is going to leave a set of attributes which is no longer a superkey. So a key is like a minimal superkey. In the previous example, student number could be a key. It's a minimal superkey. It does not have any redundant attributes anymore. It is minimal in the smallest possible form. In general, a relational scheme may have more than one key. It could be that in a relation you have more than one key, and you can basically select one of them as the primary key. So each of those keys is usually called a candidate key, and one of them will be promoted, will be designated as the primary key. That's the most important one. The primary key will be used to identify the tuples in a relation in a unique way. It would also be used to establish relationships between relations, as we will see later on. The primary key will also play an important role in the physical scheme. That means in the physical implementation of the relational model. A not null constraint will apply on the primary key. That means the primary key should always be known. You cannot have null values for the primary key, which is pretty obvious, right? A not null constraint is going to exist for all the attributes that make up the primary key. The primary key can consist of one attribute, can consist out of multiple attributes. So this is what we call the entity integrity constraint. The entity integrity constraint says that every attribute that makes up the primary key should be not null. You can see an example. So we have a car relation, we have license number, engine serial number, make, model, and year. And as it turns out, in this particular case, both license number and engine serial number are candidate keys. So one of them we're gonna promote or designate as the primary key, let's say license number, and then engine serial number is still a candidate key, but now becomes what we call an alternative key. So, but we're freely able to choose whatever we want to be the primary key. A relational database scheme is then a set of relation schemes, so you can have student, professor, course, building, and it usually also comes with a set of integrity constraints. A relational database state, remember the difference between a scheme and a state, is then a set of relation states. So it's a set of individual occurrences of each of the relations, such that every relation state is a state of the corresponding relation, and such that all the integrity constraints are respected. You can see an example of relational database scheme, again, for the personnel administration context. So we have employee, department, department locations, project, works on, and dependent. You can see all of them have attributes. All those attributes will be defined on particular domains. All of these relations will have primary keys. The primary keys are underlined. Those primary keys should identify the entity uniqueness constraint or integrity constraint, saying that the values of the primary key should always be known and cannot be null. Here you can then see the database state, and remember the database state is a set of tuples that correspond to a particular situation of the real life environment, of the real life world. Now, in a relational model, we will also be capable of modeling relationships between relations. And the way we're going to do that is by including a foreign key. Imagine that you have a relationship between employee and department. An employee works in one department. In a department, you can have multiple employees working. So I can make a relation for employee, and I can make a relation for department. For employee, I have social security number as the primary key. For department, I have department number as the primary key. And then I put all the attributes in each of those relations. Now, of course, I also want to model the relationship between both of these relations, stating that an employee can work in one particular department, and in a department you can have employees working. And the way we're going to do that is by means of a foreign key. We're going to put a foreign key, department number, in the employee relation. So a foreign key in a relation R1, and let's say R1 is employee, or a set of attributes, let's say department number in the relation R1 employee, is a foreign key if that department number that you put into employee references the department number in department. So the attributes of the foreign key must have the same domains as the primary key attributes of R2, R2 being department. So the department number that you put as a reference in the employee relation should have the same domain as the department number in the department relation. The attributes FK, department number, are then set to refer to relation R2, department. The value of the foreign key in a tuple T1 of employee should either occur as a value of the primary key of department number in department, or it can be null. It can be null if you would want to allow that an employee works in no department. So if the minimum cardinality would be 0, such that an employee can work in no department, then the foreign key can be null as well. So whether the foreign key is null, yes or no, will depend upon the minimum cardinality. If the minimum cardinality is 0, then the foreign key can be null. The conditions for a foreign key specify a referential integrity constraint, because basically a foreign key references a primary key in another relation, and it should either have values of that primary key or be null. So that's a referential integrity constraint. Here you can see another example between department and project. So you can see a project always needs to be assigned to one department, let's say minimum one, maximum one department, or exactly one department. Vice versa, a department can work on 0 to n projects. So then I have a department relation and a project relation. I cannot put department number as a foreign key, or sorry, I cannot put project number as a foreign key in a department relation, because a department can work on multiple projects. If I would put project number as a foreign key in a department relation, I would end up having a multi-valued attribute type, which is not allowed in the relational model. Remember? What I can do is I can put department number as a foreign key in the project relation, and department number is then always gonna refer to one department. So you can see project number 1000 is being done or assigned by the marketing department, department number 10. So there you only have one value for department number. Sometimes it could be null as well. If in your ER model, it would turn out that there could be projects that are assigned to 0 departments. If there could be projects that are assigned to 0 departments, then the foreign key can be null. But it depends upon that minimum cardinality, remember. So here you can see departments that work on multiple projects, like department number 10 is going to work on projects 1000 and 1800. You can also see that there are departments that work on no projects. Department number 30, which is logistics, is not going to work on any projects at all, because it doesn't occur as a foreign key value in the project table. Another example, well, this is an example of an N-to-M relationship type. Remember, an employee can work on multiple projects. A project can be assigned to multiple employees. So I could put employee number as a foreign key into project number, but if I would do that, it would not be nice, because a project could be assigned to multiple employees. So you'd have a multi-valued attribute type, which is not allowed in the relational model, remember? I can also add project number as a foreign key into the employee table, but if I would do that, I would again end up with a multi-valued attribute type, because an employee can work on multiple projects. So nor adding employee as a foreign key in the project table, or project number as a foreign key in the employee table, none of these solutions is going to work well. So if you have this N-to-M relationship type in a relation on the ER model, the way to map it is by introducing a new relation. Works on. A new relation works on which has those two primary keys, social security number and project number, and the combination of those two foreign keys, each referring to project and employee respectively, the combination is going to make up the primary key. So you can see that the primary key consists out of the combination of two foreign keys. You also have hours added to that table, which represents the number of hours that an employee worked on a particular project. And that's how you can actually work out relations between, or relationship types between relations, right? So here you can see again the employee administration example, but now with the arrows indicating the primary or foreign key primary key relationships, right? You can see all the foreign keys referring to the primary keys. Yeah. You see, for example, in the employee relation, you see super social security number referring to the social security number of that particular employee table, right? So it basically is a foreign key referring to the supervisor of a particular employee. Department number is being referred a lot, is being referred from employee to specify the department employee is working in. It's being referred from project to specify what department is working on what project, and it's also being referred to from depth locations to specify where a particular department is being situated in what location. There are more general constraints that also could be of interest in the universe of this course, but that cannot be enforced in a standard relational model. Examples are the salary of an employee should never exceed the salary of his or her supervisor. This is an example of an integrity constraint that you may wish to model, but you cannot add it as such to the relational scheme. An employee should always work in a department he or she manages. Again, that cannot be enforced. Employees should work on projects assigned to departments to which they belong. Same example we had earlier in the ER and the ER model. We cannot enforce it here. Students should not take more than 6 courses per semester. Again, we cannot enforce that. All of this can be enforced by means of extensions to the relational model. that will allow us to do so. But that will be discussed in a later chapter of this class. A popular construct here are triggers, for example, that allow us to add more semantic rules to the underlying data model. Brings us to a second part in the relational section, which is a very important part. That's normalization. And normalization is a series of steps that you're gonna go through in order to make sure that you have a good relational database scheme. A good relational database scheme means that you have a database scheme in which all relations are normalized. Now, if your relation schemes were generated from an EER model and the translation rules were applied correctly to translate the EER model to a set of relations, then the relational scheme will be automatically normalized. If the relation scheme was not derived from an EER scheme, a formal normalization mechanism, which consists out of a series of steps that we're going to clarify in a moment, needs to be applied in order to end up with a set of relations that are in a normalized form. Why do we like to work with normalized relations? So we like to work with normalized relations because then the users can clearly understand the meaning of the relations of the data, and it's very easy to formulate correct queries. At the implementation level, you will see that storage space will be efficiently used because if you have an unnormalized set of relations, it usually leads to redundancy and inefficient use of storage space. And you're going to have all kinds of risks that are going to come with it. If you have replications or redundancy, remember, there's a big risk of inconsistent updates. Here you can see a good database scheme. And a good database scheme, you have an employee relation, a department relation, depth location relation, works on project. It's a sound and solid database scheme. It's what we call a normalized database scheme because it does not have any redundancies that may lead to inconsistencies. Here you can see first of all, some informal guidelines. In a moment, we're going to give you some more formal guidelines. But in order to have this good database scheme, you should design your relation scheme so that it's easy to explain the meaning of the scheme, but also the meaning of the tables. So do not combine attributes from multiple entity types into a single relation. If a relation scheme corresponds to one entity type or maybe one relationship type, think about the works on relation in the previous example. That's a relation that corresponds to one particular relationship type. So if a scheme corresponds either to an entity type or relationship type, then the meaning tends to be clear and you're likely to end up with a good database scheme. Otherwise, if you would have a relation that is going to mix information from different entity types, from different relationship types, it may well be that you're not going to end up with a nice database model. You can see a bad database model, for example, a bad database scheme, or an unnormalized database scheme. Look at the table above. Employee department. So it's going to mix information between employee and department. And you see lots of issues with this table. You see, for example, department information being replicated. So look at Department 5, which is research. The name research is being replicated. The manager number of that department is being replicated. So imagine that at some point you would like to change the name from department name research to department name R&D. Then you would have to do as many updates as there are employees working in the research department. If you would like to change the manager number of the research department, you would have to do as many updates as there are employees working in the department. These are update anomalies. You can also have insertion anomalies. That means if you want to insert a new department, but you do not have employees yet for the department, then you know you're a bit stuck because the social security number is the primary key and you need a value there. So what you're going to do is you're going to most likely go for a quick and dirty solution and add a dummy employee like Michael Jackson with social security number 99999 and then create a department, but you have that dummy employee information that you created, which is not very nice. That's what we call an insertion anomaly. A deletion anomaly means that, imagine that you would remove the last employee from a department. If you would remove the last employee from the department, then it would mean that you also remove the department. Think about the last tuple in the employee department relation, which works or who works in the headquarters. If I would remove Borg James, that would mean I have to remove the entire tuple and I'm losing all the information about my headquarter. So you have insertion anomalies, you have update anomalies, you have deletion anomalies that all come with this very bad database scheme, which is basically a normalized database scheme. So redundancy is going to lead to inefficient use of storage space and may cause all kinds of update anomalies. Update anomalies like insertion anomalies, to insert a new employee, we must be sure to include the correct department date each time, which is not a problem in the good database scheme because there it's appropriately linked by means of a primary foreign key constraint. It is difficult to insert a new department that has no employees, which is again not an issue in the good database scheme. In the bad database scheme, if we delete from employee department the last employee from a department, from the headquarters, remember the example I gave you before, then all department data is lost, which is not the case in the good scheme. If we update department data in employee depth, for example, the department name we updated from research to R&D, then we must update it for each employee. So you see there's lots of update anomalies that come here, and we need to design the database relation scheme such that none of these update anomalies are present in the relations. Okay. A third informal guideline is to try to avoid nulls as much as possible. When I have attributes in a base relation whose values may frequently be null, it's also going to lead to an inefficient use of storage space. If nulls are unavoidable, if you happen to have a situation in which you have plenty of nulls, make sure that they apply in exceptional cases, and if needed, put them in a separate table. For example, see my next slide. So here I have an employee table, right, with social security number, employee name, office number, and assume that office number has many null values because not many employees have an office. So in this table, if you would have many null values, it would again mean an inefficient use of storage space, a waste of memory capacity. So a better alternative in order to deal with these null values could be to decompose the relation and say, look, I have an employee relation, social security number, employee name, and then an office attribution with social security number being a foreign key, so it kind of refers to the primary key, social security number in employee, and then we have office number for all those employees that have an office. So all the employees, the few employees that do have an office, will be included in the office attribution relation together with their social security number and office number. A concept that will play a very important role in normalization is the idea of functional dependency. And a functional dependency, denoted by x arrow y, between two sets attributes x and y, which are both subsets of the relation that you're working in, specifies a constraint on the possible values that tuples may have for these attributes. The constraint is that for any tuples T1 and T2 that have the same values for attribute x, so if they have the same values for attribute x, they must also have the same values for attribute y. That means that the values of the y component of a tuple are determined by the values of the x component, or the values of the x component are going to uniquely determine the values of the y component. So we say that there's a functional dependency from x to y, or y is functionally dependent on x. Student name is functionally dependent upon student number, because with one student number, I can pinpoint, or I can uniquely determine one student name. Student number 1, 2, 3, 4, 5, 6 is John Adam. Note that a functional dependency does not necessarily work in both directions. So if y is functionally dependent on x, it does not state that x is functionally dependent upon y. That's not always the case. If a constraint on R states that there cannot be more than one tuple with a given x value in any relation, instance R, in other words, x is a candidate key, think about the primary key, then this is going to imply that y is functionally dependent upon x for any subset of attributes y of R. So any attribute in a relation is dependent upon the candidate keys or upon the primary key, let's say. Another concept that will be very important throughout the normalization procedure is the concept of a prime attribute. And a prime attribute is an attribute that is part of any key. It's any attribute that is part of the key. Let's give an example, social or functional dependencies. Employee name is functionally dependent upon social security number. With one social security number, I can pinpoint one employee. But the other way around is not necessarily the case. Social security number is not functionally dependent upon employee name, because you can have employees with the same name. If you have John Adam, for example, then you can have multiple employees whose name is John Adam. So one particular value for employee name, John Adam, can lead up to various social security numbers. So employee name is functionally dependent upon social security number, but not vice versa. Project name is functionally dependent upon project number. One project gives you one project number gives you one project name. Same goes for P location. Project location is functionally dependent upon project number. Hours, that means that the number of hours an employee worked on a project is functionally dependent upon the combination of social security number and project number. Hours is functionally dependent upon both social security number and project number. So in order to know the number of hours that an employee worked on a project, we need to know both the social security number and the project number. All of that will now be used throughout the normalization process. And normalization of data is a step-by-step process which will actually analyze functional dependencies between attributes in relations. And the idea is to come up with a normalized database scheme in which we have minimized redundancy and in which we can minimize the insertion, deletion, and update anomalies. If we do not have normalized relations, throughout the normalization process, we're going to decompose them into smaller relations that do meet the tests and possess the desirable properties. Sometimes, as we will see later on, denormalization will also be tolerated, because denormalization can sometimes be done for performance purposes. Sometimes you do not want to break up a relation into smaller relations, because later on, if you're going to query the relations, you need to merge them again, something we will refer to as joining, and that's not very nice from a performance perspective. So in certain circumstances, denormalized relations may be tolerated merely because of the performance issue. Okay, we're going to go through a series of normalization steps, starting with the first normal form. And the first normal form is really very easy normal form. It basically states, in its most simple way, no composite or multi-valued attributes. That's what it states. No composite or multi-valued attributes. So in other words, the domain of an attribute must include only atomic values, and the value of any attribute in a tuple must be a single value from that domain. If this is not the case, what we're going to do is we're going to take the attribute that violates the first normal form, place it in a separate relation, and hook it up with the original relation by means of a primary foreign key relationship. The primary key of the new relation is then typically the combination of the attribute and the primary key of the original relation. In a moment, we'll see an example of that. If I would have nested relation attributes, I'm going to remove them, put them in the new relation, and propagate the primary key into it. The primary key of the new relation will then combine the partial key of the nested relation with the primary key of the original relation. Lots of theory, but let's illustrate with an example. So here you see an example: department number, department location, department manager number. Is this in first normal form, yes or no? Well, you don't know unless you know the assumptions. So in order to know this appropriately, you first need to know the assumptions. And the assumptions turn out to be the following. A department can have multiple locations. Multiple departments are possible at a given location. Well, clearly this is not in first normal form, because the location is multi-valued. And according to the first normal form, you cannot have multi-valued attribute types. So we take out the location, put it into a new relation, together with the original primary key, the number. So now we have a relation, the number, and the location. But what is the primary key of this new relation then? Well, let's just scan the alternatives. Is the number the primary key? No, because one particular department number, 15, marketing, let's say, can have multiple locations. So the number is clearly insufficient as a primary key. Is the location then the primary key? Well, no, because at a particular location, Bruges, you can have multiple departments. So nor the number nor the location suffice as the primary key, so we need the combination of both. Both the number, the location make up the primary key. You can see that again illustrated in the original example. We had the number 15 being located in Bruges and Leuven, so the location was multi-valued, not very nice. We take out the location, put it into a new relation, and here you can see the new relation at the bottom half of my slide. So you see, as I said before, D number was not sufficient as a key because department number 15 has 2 locations, but D location is also not sufficient as the primary key because in Ghent we have 2 departments, departments 20 and 30, so we need the combination of both to make up the primary key. Other example of the first normal form is here. You can see employee information, social security number, employee name, D number, D name, and then project. Is it in first normal form? Well, we don't know unless we check the assumptions. So the assumptions are that an employee can work on multiple projects and multiple employees can work on a project. Now you see there, if you look in the original relation, you see that the project attribute is composite. That means it can further be decomposed into P number, P name, and hours. And on top of that, it's multi-valued, which is not very nice. So what we're going to do is we're going to take it out. We're going to take out the entire project attribute, put it into a new relation, together with the primary key of the original relation, now included as a foreign key. So we have a new relation, social security number, P name, hours. And remember, social security number in that new relation is a foreign key that refers to the original primary key. Second normal form is going to take it a step further, and it's going to look at full functional dependency. So a functional dependency, X to Y, is a full functional dependency if the removal of any attribute A from X means that the dependency does not hold anymore. So a functional dependency X to Y is then partial if I can remove any attribute A from X and the dependency still holds. A prime attribute is something we already defined. Remember, an attribute is called a prime attribute if it is a member of some candidate key, otherwise it's called non-prime. A relation is then in the second normal form if it satisfies the first normal form and every non-prime attribute A and R, so every attribute that is not part of any key, is fully functionally dependent on any key. If it's not the case, we're going to again create a new relation, so we're going to decompose and set up a new relation for each partial key with its dependent attributes. And we're going to make sure that we keep the original primary key and the attributes that are fully functionally dependent on it. So, example, here you can see an example. So, hours is fully functionally dependent upon social security number and P number. It's a full functional dependency because in order to know the number of hours that an employee worked on a project, we need to know the particular employee identified by the social security number, and we need to know the particular project number. We cannot leave out social security or P number in that left-hand side of the functional dependency, or otherwise it will not work anymore. In order to know the number of hours that an employee worked on a project, we need to know social security number and P number, so it's a full functional dependency. This is as opposed to P name. P name, it does not depend upon social security number, it only depends upon P number. The project name is uniquely identified once we know the project number. So that's a partial functional dependency because there I can leave out the social security number and the functional dependency still holds. P name is again functionally dependent upon P number. It's again a full functional dependency. Right? This is pretty obvious because P number is only one attribute, so of course you have a full functional dependency now. And this is now used in a second normal form because imagine here, in this particular case, what you will see is if you look at a relation on top, you have social security number, P name, and hours. So P name only depends upon P number. So there we have a non-prime attribute type, P name. It's not part of any key, and it only depends upon P number. It's partially functionally dependent upon a key. So P name is the attribute which is giving us trouble here, so we take it out of the relation and put it into a new relation together with P number, the attribute on which it is fully functionally dependent. For hours, this is not the case because hours is fully functionally dependent upon the key. It's a non-prime attribute, it's not part of any key, and it is fully functionally dependent upon social security number and P number, so that can stay in the relation. Which you see illustrated right here as well. So here, the original relation that was not normalized, you see on top of my slide. So you can see a lot of redundancy there because for project number 1000, each time you see the name being repeated, invest optim. So imagine that you would have to change or that you want to update the name, you would have to do as many updates as there are employees working on that project, which is not very nice, which can lead to inconsistencies and which implies a waste of storage space. So that's why we're going to apply the second normal form here and nicely spread out the information across two relations. The third normal form is then going to rely on the idea of transitive dependency. And a functional dependency x to y in a relation scheme R is a transitive dependency if there's a set of attributes z that is neither a candidate key nor a subset of any key of R, and both x functionally determines z and z functionally determines y hold. A relation scheme is then in the third normal form if it's in the second normal form, and no non-prime attribute is transitively dependent upon the key. If you would have those kind of transitive dependencies, you can decompose it and set up a relation that includes the non-key attributes that functionally determine the other non-key attributes. A lot of theory, but the best way to study this is by means of an example. So here you can see an example of a relation that is not in third normal form. Why? Well, we have social security number, employee name, department number, department name, department manager number, and you have a transitive dependency because you have a transitive dependency from social security number to D number. D number is not part of any key, and from D number to D name. So D name is transitively dependent on social security number via D number. Likewise, for D manager number is transitively dependent upon social security number via D number. So we have two attributes that are not part of any key, but which are transitively dependent upon the key. And those two attributes are D name and D manager number. So what we're going to do is we're going to take out D name, D manager number, and put it into a new relation together with the key of which they are functionally dependent. And the key of which they are functionally dependent, in this case, is D number. You can visualize again with some tuples just to illustrate the redundancy. You can see that, like for department number 10, the information of that department is being stored 3 times because there are 3 employees working in the department, O'Reilly, Bush, and Thompson. So you see the name is stored 3 times and the department manager number is also stored 3 times. So if you would like to update the manager number, you would have to do as many updates as there are employees working in the department. If you would like to update department name, you would have to do as many updates as there are employees working in the department. So it's a lot better to bring it into the third normal form, bring the D name and D manager into a new relation together with D number because of that transitive dependency issue that we just clarified. Boyce-Codd normal form is a normal form that is stricter than the third normal form because every relation in Boyce-Codd normal form is also in third normal form. However, vice versa does not apply. A relation in third normal form is not necessarily in Boyce-Codd normal form. So a functional dependency x to y is called trivial if y is a subset of x. A table is in Boyce-Codd normal form if and only if for every one of its non-trivial functional dependencies x to y, x is a superkey. That is, x is either a candidate key or a superset thereof. This is the idea of a Boyce-Codd normal form. And remember, again, it's stricter than the third normal form. Let's just illustrate this with an example. So we have a supplier relation with supplier number, name, product number, and quantity. And we have 2 superkeys there, supplier number and product number. And let's say we also have a superkey supplier name, product number. I'm assuming in this particular case that every supplier has a unique name. Then I have 2 functional dependencies from supplier name to supplier number, but also from supplier number to supplier name. So supplier number is going to uniquely determine supplier name is going to uniquely determine supplier number. Clearly this relation is not in Boyce-Codd because I have a functional dependency for which supplier number is sufficient as a key, nor supplier name is sufficient as a key. So in order to bring it into Boyce-Codd normal form, I have to create 2 relations, and I can create 2 relations and have them refer by means of the supplier number in a primary foreign key construction, or I can also have them refer by means of supplier name. So in the left-hand solution, you will see that the connection is made by means of supplier number, and in the right-hand solution, you will see that the connection is made by means of supplier name. And that's how you can bring it into Boyce-Codd normal form. So remember, it's stricter than the third normal form. Finally, the fourth normal form is going to start from the Boyce-Codd normal form, and it's going to include the idea of a multi-valued dependency. So if you have a multi-valued dependency from x to y, typically indicated by means of the double arrows, you're going to have a multi-valued dependency x to y if and only if each x value exactly determines a set of y values independent of the other attributes. So a table is then in fourth normal form if and only if for every one of its non-trivial multi-valued dependencies x to y, x is a superkey. That is, x is either a candidate key or a superset thereof, which is how a superkey is defined, right? Here you can see an example. So you have course, instructor, textbook. A course is taught by different instructors, and one course is going to use the same set of textbooks by each instructor. We have a multi-valued dependency here, and this could be nicely visualized if you work it out with a set of tuples. So here you can see it work it out with a set of tuples for this particular course, and let's call it database management, being taught by myself and Professor Lemailleux. Let's say we use two textbooks, El Masri and Navat and Chris Date. So you can see that that textbook information is being repeated there. So imagine if we would add a third textbook, then adding just one textbook or a third textbook would involve adding two tuples to the table. There's a multi-valued dependency there, right? Because given a value for a course, no matter what the instructor is, you have the same values for textbook occurring there. So in order to bring it into the first normal form, what we're going to do is we're going to look at this original table and just split it up into two parts, course and instructor, and course and textbook, such that if for this solution, for this normalized solution, we would like to introduce a new textbook for a particular course, we just have to add one tuple to the table on the right-hand side of this solution, and we're there. So we only have to add one tuple if we want to add a new course, a new textbook, instead of two tuples in the original solution. Also, if you would like to add one instructor to the course, but using the same set of textbooks, you can also do it by just adding one more instructor to the course instructor table. So you see, the below solution is a lot more flexible, is a lot more maintainable, and has a lot less redundancy. This is an exercise which I'm going to leave up to you. It's a normalization process. So in this exercise, you can step through all the normalization steps as we just clarified them. And what is really very important here is that you carefully look at the assumptions, because the assumptions are going to tell you when something is normalized, when not, when there are issues with the first, second, third, fourth, or Boyce-Codd normal form. So carefully check the assumptions. So what I would recommend you to do is you go through this exercise and then you can contrast it with the solution we have right here. Okay, so this finishes the discussion on the relational model, and remember, this is a very important model. This is a model that we're going to also use in the assignment, and which will be used a lot through the remainder of this class. It's a model that you're typically going to build from an ER model. So usually the process will start from an ER or EER model, because that's a very user-friendly model to capture the information needs within a particular field, and then you're going to map that to a relational model, which is going to sit closer to the implementation. Okay, good. We have one more model to cover, which we're going to do in the next section.